In this lesson, we'll talk about limits at infinity. So in the previous lesson, we talked about limits where infinity could be an answer. In this lesson, we'll talk about limits where we can actually take a limit as x is approaching infinity. This is a bit of a different concept. Before, we looked at values as x was approaching that number from getting closer and closer from the left and from the right. This time, we're going to look at what happens to functions as the value of x gets very large. Let's do a few examples. We can do f of, let's just say 100. That's a pretty big number. F of 1000 and f of 10,000. And then what we'll do is we'll take a guess as to what this value appears to be trending towards. Here's the values that I get whenever I plug these into the function. It's pretty clear that the values are getting closer and closer to 1. So that's going to be our guess of what's going on as x is getting very large. This is our official setup for this. So we've got the limit as x approaches infinity of f of x. This is the value that the function is approaching as x gets very large. Now we can also talk about a limit as x approaches negative infinity, which is what's going on as x gets very negative. Now in this particular problem, the answer would have been the same had you done negative infinity. Here's some notation. You can say f of x approaches L as x approaches infinity, or we can write it the way I did a moment ago, and it's the same thing. What we want to do is we want to find some new rules for how can we calculate these limits as x approaches infinity. Here's a few pictures. You'll notice in this first picture, there is this line y equals L that the function is approaching as x gets very large. As x gets bigger and bigger, what's happening is if we pick some epsilon, some value as to how far away we want the function to be from the line, there will come a point where as x gets big enough, all the values after that lie within this small interval. And that's what we're saying down here. For all epsilon greater than 0, there's some m. M is the cutoff here, where all the values after this will lie within that small interval. Similarly, for negative infinity, we could just say something negative. As the values were approaching x on the left side, there would be some point where all the values to the left of x would fall into any interval of the size you choose. We will notice this is a trend in the graph. As x gets very large, it approaches a line, but earlier on in the function, it might even cross that line. So this is similar to the idea of a horizontal asymptote. However, you can cross the line. Next example, it never crosses, it just smoothly moves towards y equals L. But in the final example, this actually crosses L over and over and over again, but you'll notice it's getting closer and closer to the line. There will come a point when all the values, though they're bouncing back and forth, are still approaching that line. Here's one final picture of this concept. We've got this line at L. We've got an epsilon, some interval around it, above and below. And eventually you'll find this n, where as far as you can go past n, the function stays within this small interval. That's the idea of the limit as x approaches infinity being a number, the idea of it trending towards something. To bring this into some context of what you've done before, it's called a horizontal asymptote, this line, every time either the infinite limit or the limit as x approaches negative infinity are equal to that number. So a trend to the right or the left could be a horizontal asymptote. Now you probably have not seen a lot of functions with two horizontal asymptotes, but this can happen. Because it's a trend in the graph, you can have two horizontal asymptotes. It can have a different trend on the right than it does on the left, and it can cross its asymptote. It's just a trend. This is the theorem that we're going to use to do these. Anytime you have 1 over a power of x, a positive power, the limit as x approaches infinity or negative infinity is 0. That doesn't necessarily have to be 1. The properties of limits still apply here, that this could be a number besides 1. But as long as you have a number over x to a power, a positive power, the limit's going to be 0 as x goes to infinity. That's not hard to imagine though, because if you think about it, x to a positive power, as x goes to infinity, the denominator is going to go to infinity, and so 1 over something infinite does indeed give you 0. I just note that all the limit laws still apply. Similarly, we'll be able to work with those. What we did in the first example was we guessed that this value was going to be 1. Let's show this officially. What we do to prove that the limit is actually 1 is we take this function and we multiply by 1 over the highest power of x that appears. The highest power is just x. We get the limit as x approaches infinity of 1 minus 1 over x when we distribute the 1 over x over 1 plus 1 over x. Now we can use the rule. Our limit laws apply, so we can just do substitution basically. What it boils down to is this is 1 over x to a power, so this part is going to be 0 when we take the limit. This part is going to be 0 also. But again, the limit of a constant is still the constant. So what we get is 1 minus 0 over 1 plus 0, which is 1. Thus, the horizontal asymptote is y equals 1. So again, we calculate the limit. If the positive infinity limit or the negative infinity limit turn out to be a number, that is a horizontal asymptote of the function, and you can have up to 2. Next example. Let's find the horizontal asymptotes of these functions, and we'll do so by taking the limit as x approaches infinity and following the same rule that I just did. I need to do 1 over the highest power of x. Take a look at it. You'll notice the highest power is actually x squared this time. Now let's just multiply through. I get 1 over x when I do x times 1 over x squared minus 3 over x squared divided by 1 plus 4 over x squared. That's what we were looking for. So we've got this number 1. There's no more just straight x's. Everything is over a power of x. So every number that's over a power of x, when I take the limit, that's going to make these go to 0. I get 0 minus 0 over 1 plus 0, and if you calculate that, you see that the answer is 0. So what that means is the horizontal asymptote is y equals 0. Next example. We're going to again take the limit as x approaches infinity of this function, square root of 4x squared plus 3 over 3x minus 1. The question that we have to ask ourselves is, what are we going to multiply the top and bottom by? Again, it needs to be 1 over the highest power. But what is the highest power? In this one, it's just x to the 1. But in this one, it's the x squared under the square root. But if you think about it, the square root of x squared really is just x. So I'm just going to use x for my power. However, for it to be compatible, I'm going to write this one as 1 over the square root of x squared. Very important to note right now, these are the same thing. You are multiplying by the same value. On the inside of the square root, I'm going to multiply by 1 over x squared, giving me the square root of 4 plus 3 over x squared. And in the denominator, I'm just multiplying by 1 over x, giving me 3 minus 1 over x. Same rule applies. If it's any number over a power of x, it just becomes 0. So we get the square root of 4 plus 0 over 3 minus 0. Square root of 4 is 2, and so I get 2/3. Thus, the asymptote is y equals 2/3. That one was a little bit on the tricky side, but just remember that the square root of x squared is just x. Now, I actually claim I missed something in the last problem. Remember that the horizontal asymptote can occur at positive infinity or negative infinity. Let's go on to the next slide. Turns out there is another one. So we're going to do something similar. I'm going to do 1 over x again. This is the same thing, but I'm doing negative infinity. Now, the last time I did 1 over the square root of x squared. But this is actually incorrect. And let me prove it to you. Pick your favorite number, some negative number, because x is trending towards negative infinity. I'm just going to use negative 1 for this example. In the case of negative 1, I'm doing this. Negative 1 squared is 1. And so I just get 1 when I take the square root. But I started with -1. This does not equal x, which is -1. So what's going on here? When I plug in a negative value for x and then square it, it becomes positive. When I take the square root, it is still positive. So what it boils down to is the square root of x squared is actually not x here. It's the negative of x. So to correct that, I put a negative sign in front. Let me give you one more justification for that. The negative of the square root of x squared is actually the negative absolute value of x. Think about what I just said a minute ago, that if you square a number it becomes positive, and you take its square root it stays positive. Whether it was positive, it's still positive. If it's negative, it also became positive. So I have the negative absolute value of x, and finally, if you know the official definition, when x is negative, the absolute value of x is just making it positive, but that's the same thing as the negative of the negative, and so we just get x. Consequently, negative square root of x squared is equal to x when x is negative. Now this is a bit of a hard thing to understand at times. It's a hard justification. If it's a little bit complicated to you, feel free to bring a question about this to class whenever we talk about this lesson. And note that whenever I deal with a negative infinity and an x squared inside, it's always going to be negative square root of x squared. With that said, we get the limit as x approaches negative infinity. The negative sign is on the outside of the square root and will stay on the outside of the square root. 4x squared divided by x squared is 4. We get plus 3 over x squared. And the 1 over x still gives me 3 minus 1 over x. Same thing applies as before. We get zeros wherever you've got a number over a power of x. And now, strangely enough, I get negative 2/3. So the other asymptote was y equals negative 2/3. Kind of surprising. This is an example of a function that has two horizontal asymptotes. Let's continue with a bit of a different one. So now let's look at how can we do some infinite limits with some of the strange examples. This one's actually not hard, though it is strange. Think about the graph of y equals sine of x. As x goes towards infinity, does the function really trend towards anything? No. It just goes and goes and goes up and down and up and down and up and down and up and down, and it never trends towards any particular value. This limit does not exist, and the official justification could be uncontrolled oscillation. It's actually the same exact idea as the sine of 1 over x was when x approached 0. Next one. Now this one, if you really plug it in and try, you're going to get something like infinity minus infinity. Now, that is not 0. Infinity minus infinity is a nonsense expression, just like 0 over 0 is. Eventually we'll call these indeterminate forms. But what it boils down to is that infinity minus infinity is unknown. We can't do it just by thinking of it that way. So what I'm going to do is I'm going to use a strategy similar to what I did for other problems that looked kind of like this. The conjugate. 4x squared plus x plus 2x over the square root of 4x squared plus x, again plus itself, the 2x. Multiply top and bottom by this conjugate expression, and that's actually going to make this limit work. If you'd like, you can do an over 1 here, if that helps a little bit. And we get the limit as x approaches infinity. Again, this is like an a squared minus b squared. The first term is 4x squared plus x. The square roots cancel. The outer term and the inner term cancel each other out, but the last term is a minus 4x squared. In the denominator, I get the square root of 4x squared plus x plus 2x. These cancel out. Let me write this below. I'm left with the limit as x approaches infinity of x over the square root of 4x squared plus x plus 2x. To do this one, I'm going to need to multiply by 1 over x on the top and bottom again. And when I do this part inside the square root, I'll treat it as square root of 1 over x squared. Just keep in mind we are going to positive infinity, so nothing strange is happening. Anyway, we get the limit as x approaches infinity of just 1 over, here I'm dividing by x squared, so I get 4 plus 1 over x. But outside the square root, it's just going to give me a 2. So now we can apply the rules. This is a bit of a long problem. We get 1 over square root of 4 plus 0 plus 2, which is 1/4. Bit of a complicated limit, but as you can see, our algebra techniques are sufficient to solve it with what we already have. This last slide has just given us some ideas of sometimes the answer to an infinite limit is infinity or negative infinity. If you take a limit as x approaches infinity or negative infinity, you really wouldn't expect to get a number answer very often. I have a definition up here. Feel free to read and look over it. This is a similar definition to everything we've done before. We're just putting infinities together. Let's take a look at the graph of x cubed. It makes a pretty good bit of sense to look at this and say, well, as x goes to infinity, x cubed is going to infinity, right? The graph is rising without bound as x rises without bound. Similarly, as x falls, as x is getting more and more negative, the graph falls without bound, and we'll call it negative infinity. Then we get to this last one. Now I don't really have a graph of this showing, but we can attack this without a graph. If you look at it directly, it looks like infinity minus infinity again. So now I need a new strategy, and here's a strategy you can employ. Factor out an x. Now look at it. This is going towards infinity. This is going towards infinity. And consequently, you really get something like infinity times infinity. Again, I don't write that sort of thing, but it's pretty clear if you take an infinite thing times another infinite thing and they're both positive, you're just going to get positive infinity.